Thanks for this opportunity to present the second part of the tutorial. My name is Ashvin Mahajan. I work for Cinero, and I'm in the turbo machinery group. And just a slight overview of what we do. Our background is mostly on in turbo machinery structured multi-block meshes, and we use the Onera code ELSA, but it's part of a long-term plan is to have a dedicated open source solver for our turbo machinery applications. And that's why within the group, we've started working on SU2. And today I'll be presenting the stuff that I've been doing, setting stuff up for our major goal is to plug SU2 into a big design chain. So that we can do shape optimization of blades and wall profiling like in turbines and even compressors. So we have a pretty ambitious objectives using SU2 within our design framework. So today's talk is basically going to be the axial compressor R37 and just a slight overview of what you need to watch out for and how you set it up. And I'll start. So one of the main objectives is that normally you will have an inlet profile that you have to interpolate into the inlet plane. And so SU2 has the capability to do that. And I will show how a user can do that. And it will be a step-by-step procedure that I'll go over. A lot of the details about the config file card has been gone over by Alessandro, but I will also touch upon it. And these are just links for your convenience. This is the main build, and this is the branch by Josh Kelly, which will require compiling. The other one is has pre-built binaries. There's not, you can still run the test case, but I will show you what you have to comment out. And the major difference is going to be regarding the outlet, the log file, because the log file from Josh's build is primarily for turbo machinery. So here's the summary of steps that we go through, and this, if you guys want to do it hands-on, you'll need to download certain files. So you can download the mesh from this link. Do they have the? Yeah. Okay. You have to make it in the full slide and then link. Yeah. And this is, I will be going over the CGNS, GMS page part, but you don't have to download this. This is optional. You have to download the config file, and you have to download the input file.dat. This is really important. And it starts from the hub and goes to the radius, and where we define K and omega for the SSD. And this is for your practice. When you have the requisite Python modules for plotting the radial profiles that SU2 spits out into a particular directory for turbo machinery called turbo machinery. And I use these scripts, so I thought I'd just upload them so that you guys have those who want to do the radial profiles have a leg up and they can start off, and it can do multiple plots with different colors and stuff like that, but the user can modify it. So for the scripts, you need Python 3. Just for your information, you need these following modules. And this is a picture of how it's what you need. These scripts I use for the radial profiles and for the history, the convergence history. So, and they come in pretty handy. So now we can go to the R37 compressor example. So the mesh, we use Cadence AutoGrid for all our meshes. So it's a multi-block structured mesh. And so once you get the CGNS file, we export the CGNS file, and then I import it into GNSH. But this is something that all of you have to pay close attention to, is that you have to use this particular version. It's an older version. Why? Because the newer versions, there is an issue with the CGNS import where the surfaces are patched. They're not homogeneous. Like for example, the periodic plane surface will have different colored patches. So if you select that, the periodic plane and you mark it, it won't be complete. And so SU2 will have an issue. So we have reported this, but so you have to use this 4.4.1. So what we do is we import the CGNS into this version, and then we tag the surfaces, which I'll show you, and then we export the SU2 mesh. You can do it via the GUI or with a script, and I'll show you that. So for this particular, I mean, in general, this particular design point has a RPM of minus 1800 radians per second. The blade has 36 blades. What we call the periodicity is 36. One of the design points, the corrected mass flow was 20.60 kilograms per second, and the 95K Pascal outlet pressure is close to surge. But I mean, these are just references for the ISO line that I will show you later on. I went from 75K to 140K. For the inlet conditions, so basically the main part of this talk is how to import an inlet profile. So that's normally what we do when we do design optimization at Cinero with ELSA. So and for that you need we put the total temperature, total pressure, we have the radius, we have the alpha and the phi, the incidence angles, as well as the K and the omega for the SSD. It's not much different than what we used in ELSA. So that was a big plus because it was easy to get going. So here's just a refresher for those people who want to use GMSH to import in a turbo machining mesh and how the tagging is done. So how to tag surfaces for markers and export an SU2 ASCII file for simulation. So we use the mouse. Normally, right now we're doing it interactively. We use the mouse to tag and name the different surfaces, and then we generate a script, and then you can reuse the script if the surface numbers don't change. And then you use this particular command in your terminal to export the SU2 mesh. So here's what the single row mesh would look like with one blade, and this is the script file that you get from GMSH when you first interactively tag, and then you save the geo file, and then it has all the requisite surface numbers. And then when you run your SU2, the config file, it shows you all the different assigned boundary conditions and their marker names. So as you can see here, I have PER1, which is periodicity 1, periodicity 2, which are the two planes, inlet, outlet, then the blade, shroud, hub upstream, hub downstream. And the picture below is basically the menu where you use, so you use physical groups and you say add surface, like this, and then, so this is an overview. Let's look at, if you guys have any questions, stop me now. So this is the SU2 file, just Alessandro went through it, so I'll go over it again. So the important thing is that when you do 3D geometries and with the GMSH export, you need to watch out that the end dyne should be equal to 3. If you do not assign, let me go back. This is important. If you see this part here, the physical volume basically assigns all the different blocks that you have. Now, if you incorrectly define this, or you forget to define this, the script doesn't have this, then what will happen is that end dyne won't be equal to 3. So when you try to run SU2, it won't work. So that's something important. And then you have the number of elements, and then you have each boundary is, so you have 9 boundaries, so its end mark is 9. And then you have a marker tag with each boundary that you have assigned a distinct name, and then the number of elements. So normally when we generate a new mesh, we go through all this just to see that everything has been marked correctly. So for this tutorial, we're just using a very coarse mesh, a super coarse mesh. It has no fillet, and the links are there to download the mesh. And it's only to be used for learning. It's not to be used for validation or anything else. It'll work on your mobile workstations. So just a refresher on what Alessandro touched upon with the assigning the boundary conditions. So we have marker heat flux and we have marker periodic. Because in turbo machinery, normally you don't want to do the full annulus. So if it's a RANS computation, we're assigning the periodic boundaries. So I don't think you guys can see it. So here, so the marker heat flux, you assign the no slip walls, and then in the marker periodic, you define your periodic boundaries with the assigned rotation. So in the z-axis, 10 degrees. And this is how it looks when you're in GMS space, once you have tagged your surfaces. So you have shroud, hub upstream, hub downstream, you have inlet, outlet somewhere here. Then you have a blade with the blade tip, because this R37 has a tip gap. And then you have the 2 periodic boundaries. So this is a picture of how the boundary conditions are set. So you have the inlet, hub upstream, the shroud. So you have the blade, suction side, pressure side, and the tip, which are rotating. So the blue parts, so in absolute frame, the rotating parts and in gray. This is from ParaView. So you have the inlet, and then you have the 2 periodic boundaries, and then you have the outlet. And the hub end wall, if you have a fillet, you have a fillet which is rotating. So this is important for those who are downloading the pre-built binaries. So for the turbo machinery branch of SU2 VA, we have a turbo performance kind, which tells it if it's a compressor, turbine, if it's centrifugal or something. So you need to, for the main branch, you need to comment that out, and in SU2 the comments are with the percent sign. So now we get to the main thrust of the tutorial, which is how to import an inlet profile. So now here we have so the inlet type is marked set as total conditions. So we are importing total temperature and total pressure, and it'll ask you specified inlet profile, and you say yes. And then it says what type of interpolation do you want to do. You can do linear, cubic, or a schema, but normally we stick with linear. And then the second part is the alpha feed, your incidence angles. And then it'll ask you if you want to print the inlet interpolated data. And normally you can say yes, but you do have to do some work plotting the data, because sometimes the rows and columns get kind of mishmashed. So, and then this is just a generic setup for the marker inlet. If you comment this out, then it'll ask you for this. But the inlet conditions are basically set by the inlet profile. And here's the file name that you would import. And then when you run SU2, it'll tell you that what file it has imported and and what type of interpolation that you've asked for, and if the interpolation has been successful within the requisite degree of tolerance. This here is the inlet matching tolerance, and sometimes, so here it's 1 × 10⁻⁶. Sometimes you will have to play with this, depending on your problem. So you'll, I mean, sometimes it can misfire, so you'll have to look at this, and you may also have to look at your shroud and your hub radii and see if they are outside or inside the bounds of the interpolation. So like I said, some playing with the radius of the hub and shroud may be necessary. So in mark 1 says that you have one inlet marker. So here's an example of the file. So you have the radius here, and your total temperature, total pressure, the alpha phi, and your K and your omega. And you have number of rows and number of columns. You have to specify these. So now we come to the outlet marker for this case. So we use the Gill condition, and we impose static pressure with radial equilibrium. So go over here. So outlet, radial equilibrium, and then you give the outlet static pressure. And since there was no reflection, I put spatial Fourier as no, but I am going to do a series of cases, compare the isolines with spatial Fourier with yes, just to see the difference. And then the Gill extra relaxation factor, I will touch upon, it's in the appendix. This basically affects the type of the static pressure at the outlet, the curve, the linearity or the degree of non-linearity of the curve as it approaches either the shroud or the hub. But we'll talk about it later. Because originally for my study, I was trying to match the SU2 simulations to not only the experimental data, but also the ELSA. So I was predisposed to a slight prejudice because I wanted both to be somewhat similar. So I had to play with this factor. So this basically the factor, there's one column for under relaxation, and the other column is the degree of percentage you want to apply it over the radial distance from the hub and the radial distance from the shroud. So when you run SU2, it'll tell you that you're using the Gill's boundary condition at the outlet. So now we come to the part where if you downloaded it, you can run it, but it's still not ready because I kind of wanted to small little exercise. So the name that I put in is kind of a bogus name, so that the users could find where to look for the name of the mesh. So the name of the mesh that you imported is r37_course.stu2. So you use your editor to put that mesh file name in here instead of this long one. And then to launch the simulation, like Alessandro showed, like in my case, in my Linux machine, you have a path, and then you do SU2_CFD R37 underscore from scratch, and then you launch it. So do I wait till or do I come back to this? People are running. Is anybody running it or? Okay. Just should I continue? Okay. Did you change the name of the mesh file? Is it working? Okay. All right. It's not going to convert to bits. It's a really coarse mesh. It's just the demo to spit out stuff.
No, I don't. Yeah.
So if you run it normally, like as Sandra mentioned, you will have a history.csv file, and if you standard output to a file, if you want to basically make plots of the ISO line for different pressures and output pressures or mass flows, then you need to output the data into a log file so that you can extract the relevant information and then plot it. And then you'll also have a volume and surface files in BTU format for ParaView. And ParaView, like you know, is open source. And for V8, I think 6751, I think, the radial profiles can be found in the turbo machinery directory that it creates when you launch. So do you have it for the turbo machinery directory?
Yeah.
Okay, and so you can, so if you CD into the turbo machinery directory, you will see inlet and outlet span-wise thermodynamic and kinematic DAT files in column format. So pretty much those are, you use a Python script. You could use your own or the one you download to plot the values in those files to look at the radial profiles. So in my study for the fine mesh, I used, just to show the how SU2 behave, I used the Cato Lauder option for SSC 2000, V2003 on the fine mesh, and it compared well with the experimental data. So just so the gold crosses are basically your experimental data, and the black line with the circles are the data extracted from SU2, the ISO line values from SU2, and the blue line is basically the output from our own Scenero post-processing card, where we weighted with the mass flow. So you can see that both results are somewhat similar with the experimental data. So this was pretty encouraging. But I highly recommend you use the V2003 version of SST. The 1994 will not give you this ISO line. It'll be way lower. In fact, yeah. So this is really encouraging. So now I'm going to go to the next step in my study, which is building the chain for the optimization. So I was pretty happy with this. So right now, if you have any questions, there'll be, as I go along, I'll start uploading detailed slides with a lot more information. And you guys are free to ask me questions, even email me, because that's the only way even I will learn from people's questions. I'm also learning. And for turbo machinery applications, I strongly advise you to use the SU2 branch for turbo machinery, the V8 branch. Thanks, but I have the appendix here. So this is some extra stuff that I would like to talk about, the Gill's extra relaxation factor settings. So this was, and then the simulation steps, the fine mesh study, because the fine mesh will be available on the portal. for people to download and build their own isolines, and some overview of the post-processing. So this is the extra relaxation factor. So basically these two. So the first value is your under relaxation, and this is your depth from the shroud and the hub where you want it to apply it on. So this is the nominal curve where you didn't do any modifications. It's the stock setting from what you get when you download uh, uh, the card. And this, so no, sorry, this is the nominal one. But when you play with these values, it pushes this curve here, makes it more linear. So when I had this setting at 0.5 and 0.5, I had this kind of profile, which I didn't want. So I had to play with this to move this profile to slightly more linear towards the hub. So you guys need to play with this relaxation factor. So now we come to the simulation runs for the fine mesh. So the fine mesh is available, and that has a fillet. So here you have to do it in 2 steps. You have to run the first order row scheme, and then you have to restart it with the row plus muscle scheme to make a second order. Otherwise, it won't. You'll have issues with convergence and it'll crash. And this is how you can start off with the SSD with these settings, but now in V8 it's default, so you don't need to put this. You can just put the Kato lambda, and this is how you set up to the second order. So this is the log file that we get from the turbo machinery branch. So all your relevant data based on the number of the frequency of your writing to the log file, you get it like this. And this is more turbo machinery specific. And then you can extract the values to plot for your post processing of your ISO lines. So you'll have your efficiency, total pressure ratio, inlet and outlet mass flow for the passage. And this is your iteration time. So for the residuals, the Python file can plot your residuals, and from the history.csv. So this is from the log file, and these are the residuals from the history file, and the mass flow is also from the log file. So there's a lot of ways to skin the cat. It's up to you. But I use these to see how the simulation is progressing. And this is an example of the history file. And this is a sample of the radial profiles that you can plot from the turbo machinery directory. So here I'm plotting an example of plotting radial profiles at the outlet. You have the total pressure and total temperature. So it's the available data is in the turbo machinery directory. Every time you run it, it gets, I think it overwrites the files, but the first time you run it, it'll create the directory. And you look for the kinematic and thermodynamic values. The kinematic values will have your momentum, tangential velocity, radial velocity, your Mach number. And the thermodynamic will have your density, total pressure, static pressure, and so on. So now, if you want to go, I mean, there's the other way to do it is you can assign an outlet plane that you only want the to plot, and then you assign an inlet plane and then you run the SU2.solution config file, and this will create two separate surface files in either VTU format or TechPlot format, and then you can go in radially in a stack way, create your own radial profiles if you don't want to depend on SU2. And for plotting surfaces, normally now we're going to use ParaView because we don't have TechPlot. So, and we're going to, so for the ELSA computations that we have been using, we use Insight. So we have a whole really big suite of modules for plotting in Insight. So now I have to do something similar for ParaView for SU2 so that you have pre-solver and post, and you put the whole thing together. Yeah, that's it. So if you want hands-on. You have any questions? Yeah.
Just briefly, the other story, I suppose, the advantage of using this, just using that total pressure temperature condition.
Well, the thing is that normally it's in industrial applications, and there's a specific. It's not a fixed scalar value. It's like in the wind tunnel when you're testing an engine, you're going to have a profile. You're going to have variation, radial variation from the hub to the shroud. So it's normally for the large bypass ratio engines, it's a customary practice to do that. I think for the turbo machine, the centrifugal compressors, like for cars, like turbo, you can have a scalar value, but for the big engines, you need it's basically standard practice to have a profile. Yeah. No, I mean, I looked at the convergence. I think, so you're asking, was it hard to convert second order, or why did I use?
No. In general, the process. To which second order
Normally we do start with first order to go to second order. It all depends on the initialization of the flow, the turbulence intensity and stuff like that. So the first order sets it up for second order. So
you have to make them to the Appendix coefficient.
no, I didn't. No, I didn't dabble with that. Basically, what I did was try to get a good solution at first order, and then ran it with the second order. I mean, I tried, like you mentioned, Jameson JST, but no, it's row with muscle was more stable. And then I looked at the mass flow so that it's.
So you
Yeah, yeah. Well, with JSD I was not successful. Yeah. Well, I couldn't get past very much, so I stuck with row and with the monotonic. The limiters, yeah. I mean, I tested both Venkatakrishna and Van Albada, but the thing was that I was benchmarking with ELSA and how, because the ELSA study on R37 was, they had published a paper, the team had published a paper, so they used Van Albada. So then I was trying to go as close to them. The only big difference is that they went with K epsilon, which is easier to, at SSD, you still have to, I mean, I mean, at least with version 2003, it's more encouraging with the Kato louder. But 1994, my values are totally off.
No, because it seems they're recruiting for both of these is not that big newspaper a few years ago.
For the
So that's why.
For the convective gradients, I use green gauze, but I have also used weighted least-squares, but I don't see, the differences are not, earth, I mean, they're not not much, so you can go with either.
But if you try variables, like an open mesh.
No, 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 okay.
If you reduce it to actually.
Maybe with this course mesh, I'll try it. Okay.
You go like 1/3, like an oil mesh, just like a couple of meters around.
Okay.
When you're doing multiple checks to set different design ratio. So in that case, JST works.
Okay.
Now set mesh is different beyond which JST becomes.
The thing is that the internal, see, we have total of 6 users of SU2. And so I'm mostly using it for turbo machinery, which the JF and JF, my colleague in the back, he's using it for external flow, like airplane body wing. And then there are other groups who are using DDS. So their experiences are different in the sense, like what works for them doesn't work for me. Like some are using JST and he says, no, it works fine for him, but when I try it, it doesn't. Internal flows, you have to be a little more, they're more sensitive. I mean, I'm not, I don't want to be misquoted. It's my experience. I think
Yeah, I'm just curious, sometimes I see a lot of 2D, like turbo setups, things like a hybrid mesh, and a lot of 3D ones structured meshes, so I'm just curious, like, why you structured for 3D and like a lot of the 2D ones see this like mainly hybrid, you know?
Well, actually, for turbo machinery, I mean, originally 2D is, 3D structured multi-block is more efficient, and it captures it. In the past, it was more, it had higher fidelity in capturing the separations. But now, even in 3D, when you have complicated cooling channels within the blade or within the hub and the shroud, and you have squealers and stuff, and then you're adding more geometrical effects like piping, and so now it's becoming more hybrid.
Yeah.
So it's now the unstructured meshes are becoming more applicable in 3D configurations.
So before it was sort of like structured one.
The structured ones, there was a case of efficiency in terms of the computational time. Plus it was in terms of, in turbo machine, the mesh quality, it's very sensitive to mesh quality.
Yeah.
Like when you use, I mean, like for example, Cadence Photogrid is basically this industry standard, at least in Safran, for generating meshes for fans, turbines, compressors. I mean, it's so, and it's scripted and automated, and it's basically multi-block. But now, now there is the unstructured meshes because of the you want to add in more geometrical effects within the blade configuration. So the unstructured meshes are being used more, but near the boundary layers, it's mostly structured.
Yeah.
Yeah. But yeah, in 2D cases, like, yeah, I mean,
It doesn't matter too much computation to response faster.
well, if you cannot, I mean, if you don't have multi-block automation, then normally, like in GMS, like we have people using LES and stuff for like for a 2D case, and they normally use the boundary layer structured and a hybrid unstructured, because the important part is getting the boundary layer right. But also on both, and I kind of prefer unstructured meshes. I used to do multi-block meshes, and there's a certain art to I used to use GridGen, the original pointwise. Those are the Friday nights. I was in the lab using it because my professor thought I was addicted to it, and she said only Friday night you can go in the lab and use it. I was a total nerd. Yeah.
Thank you.
Thank you.
You mentioned that you use enzyme.
Yeah.
What features are missing in paragraph? So what is hindering you to meet your visualization?
I think, well, I've built over the years a whole suite, I mean, a huge library of stuff for Insight. And it's just that I'm still learning the scripting language. It's not that straightforward as Insight. So it's just a steep learning curve right now. But the big advantage is it's since it's open source, it has a real good, I mean, place. It's just that it's hard because it's like I'm used to building everything in Insight, and structured multi-blocking is I mean, like for example, like when Alessandro showed, when you do the radial cuts, it's no brainer because your radial cuts is based on your IJK coordinates. If your radial distance is in the J coordinate, then you just select the J coordinate and it'll do the cut, and then you have your blade to blade. Whereas now in unstructured meshes, you have to go into the math and you have to script that whole thing. So I have to build this whole thing, and it's just I think it's just a question of experience. Jeff can add, he uses ParaView a lot for the wing body stuff.
Yeah, because for my experience, I use a lot of the hack for some reason, yeah, to argue. And I've not come across anything like that. So I'm always wondering.
You will have that, yeah, it is I mean, TechPlot, yes, TechPlot has a large, like Insight, you can do a lot. I mean, like what Alessandro showed, and I had experience with TechPlot previously in school. ParaView it's very powerful, but it has a steeper learning curve. You need to, but the other issue is when you come from Insight and TechPlot, you are predisposed to a certain prejudice, like structured mesh and unstructured. So you have to disassociate yourself and start from scratch, you know? So, like my problem is, like I said, okay, I can do this as Insight, I want to do this as ParaView. So then there's that problem. So it's just a matter of time. But it's I mean, like, it's not like it's very powerful. People are doing a lot of great things with it, and it has a lot of tools and libraries. It's just a matter of getting dirty and sweat and blood. There was that old joke of CFD. In my time, CFD stood for continuous Fortran debugging. This is a 90s joke. Yeah. Yeah, colorful.
Yeah, sure, yeah, same way.
Right. Just say that if there's no more questions, we can just thank Ashvin and go ahead and
All right.